If you'd like to join us live, we're in building 481, room 1207. And today I'm happy to have with us Dr. Avinash M. Dangare, who is an associate professor in the Department of Material Sciences and Engineering at the University of Connecticut. He received his PhD in Materials Science and Engineering from the University of Virginia in January 2008 and carried out postdoctoral research through the National Research Council Research Associate Award from the U.S. Army Research Office, and is a senior research associate at North Carolina State University before joining the University of Connecticut as an assistant professor in 2012. He has been the recipient of the 2015 Young Leaders Professional Development Award from the Minerals, Metals, and Materials Society and the 2015 National Science Foundation's NSF Faculty Early Career Development Award. Avinash currently is a co-PI of a DOE NNSA Center of Excellence led by Texas A&M University, focused on the dynamic deformation of solids. So today's talk is being recorded, and also please be aware of any export control issues, and it is an unclassified meeting. If you have any questions and you're online, you can put it in the chat field and I will read them at the end. And if you're in person, just make sure I give you the microphone before you talk. Otherwise, I hope everybody enjoys, and please take it away.
Thank you, Paul. Thank you, Paul and Allison, for bringing me here. You can come in. Yeah. So my talk is basically demonstrating a virtual framework, and this is something of interest for me. My primary expertise or experience has been in materials modeling across different length scales. And for the past few years, as part of the NNSA Center, which is CREDS, the Center for Research Excellence in Dynamically Deformed Solids, which is led by Mike Demkovich, and we co-PIs are Amit Mishra, Irene Beerline, and me at the four institutions. So as part of the center, I carried out experiments. This is at the dynamic compression sector, as well as some experiments at Johns Hopkins University, which basically started getting me to think, can we actually model these kinds of experiments? Which allows us to actually predict what may be happening in real time, so that you can use that to complement experimental analysis and stuff. So this work has been done in several parts. Most of my students, Avnish is was a postdoc in my group. Currently, he's a director's fellow at Los Alamos. Marco Echeverria is a graduate student who's currently going to finish. Kerma is also another graduate student currently going to finish. Sergey was a graduate student who finished a year ago. So these are all capabilities developed by these students. And I have the pleasure to basically summarize where we are going with this and what we can achieve in this work. So my focus on laser shock experiments has largely been in terms of small system sizes. These are experiments where you would like to do in situ characterization using diffraction, or you basically want to look at materials at extreme strain rates of loadings. You're looking at 10 parts 7 per second and higher in that sense. So there are two ways to do laser shock, where you have a direct laser drive, where the laser is actually interacting with the metal, generating a plasma ablation of the material and driving a shock wave to the material. And you can basically use real surface velocity profiles, which are here. And you can look at spall strength, shock velocities, Hugonian elastic limits, all those kinds of things. And you can basically correlate the spall strength as a function of grain size, or spall strength as a function of strain rate, and all of these kinds of phenomena, which basically allow you to predict dynamic deformation. Another more recent effort has been at Johns Hopkins, where they actually drive a flyer plate into a sample rather than directly having the target irradiated with a laser. And so this is, again, a concept where the laser is interacting with another flyer. And these are the experiments I've been doing. I'll talk about this a little bit. So the idea is, what information can we extract out of these experiments? So if you want quantitative information on how does plasticity evolve in these materials during these interactions, you basically have to use something called as in situ characterization. This is using diffraction. Either you can have these spots, or you can look at intensity profiles. And these techniques are, again, very, very controlled experiments for small system sizes. So the idea is either you can identify what modes of plasticity are playing a role in the search. So you can have dislocation-based plasticity, and you will see peak broadening, basically. You can have deformation twins, and you'll see peak splitting, like you'd see over here. Or you can have phase transformation, and we'll basically see an appearance of new peaks in these, or in the lower diffraction patterns. But this only tells you that these are the current operators at a certain time. You don't get information on how much plasticity is happening, how much dislocation density versus twinning versus phase transformation is happening. And a lot of the challenges in the interpretation are based on what is the time that you're characterizing these microstructures. And I'll explain that in a little bit. So you can look at diffraction patterns, you get new insights, but a lot of the contributions from plasticity, you have to do shock recovery experiments. And you look at the microstructures after they have been shocked, and you say, okay, we do see a lot of twins in these microstructures. This is tantalum, this is molybdenum, and this is iron. So definitely when the shock wave went through the material, you generated a whole lot of twins in the microstructure. The question is, are these twins the same fractions that you would have during the shock compression, or is it that some of these twins that are at a shock compressed state go away as the material goes back to zero pressure? So that kind of quantitative information is lacking if you're only looking at shock recovered microstructures. So we don't know at different shock stresses how much more twinning do you get, or how much more dislocation density do we get. So the quantification is still a challenge when it comes down to doing experiments. So I'm primarily a computational person, but my limited experience was at DCS. And these are the experiments we ran. We used the 100 joule laser system over there, which I use as a 10 nanosecond pulse. We basically took about 25 micron thick foils so that you can get nice diffraction patterns. We had a nice grain size to the system. This is a wheel where you can generate a lot of shots. And you can generate diffraction patterns, like this is the ambient diffraction pattern showing BCC peaks. This is the shock compressed diffraction pattern. And you can basically start indexing these peaks based on their positions in that sense. So you can distinguish between an ambient and a shock microstructure. And you can see, okay, you definitely see this is phase transfer. But now the question is, if you are not taking the diffraction pattern when the whole system is completely shock compressed, it is very difficult to identify how much of it is phase transformed or how much of it is in a shock release state. And we learned that through experience, because when you build these samples, there's a thick layer of epoxy on each side, and that thickness of the epoxy will decide whether or not your timing is accurate or not. So if you don't get the diffraction pattern at shock breakout, you're going to be in a complex state of stress. Either you can be partially compressed where the shock wave has not reached the back end of the sample, or you could be in a partial release state where the shock wave has gone past the end of the sample and you have a release wave coming in. So that limits your capability to quantify based on the peak broadening or the types of peaks. So are these just pure FCC, or are these a combination of FCC and BCC or HCP peaks over here? So we can basically start looking at these peaks and say, okay, at a pressure of 45 GPa, let's say, these are the peaks of the BCC phase, these are the peaks of the HCP phase, these are the peaks of the FCC phase. And you can start making some correlations, but there's no way to identify how much of it is actually phase transform. So having a modeling background, this is what we figured, okay, we need to come up with a capability that we can actually run these kinds of experiments. The other set of experiments I did, this was at Johns Hopkins. This is a laser-driven flyer. The idea is you have a flyer, which is typically an aluminum foil, and you shoot it with a laser, and that gets accelerated onto a target over here, and that will generate like a micro flyer plate impact test. So the flyers are typically anywhere between 25 to 50 microns. This is my flyer stack over there. So the small ones are the unshocked ones, and these are the ones that are shocked at the end. And the idea is you can basically have the flyer, you irradiate that with a laser, you can choose the energies, and you can see that the flyer is basically ejected out like this. This is very cool, and you can actually see something ejected out. Typically, the target is somewhere over here. They have a flight distance about 250 microns so that you get peak velocities. But if you look at the velocities of the flyers at different energies that you're depositing, you have an increase with fluence, but it kind of starts to saturate over here. The question is, why does it saturate? Why do you see this increase? Is this because of the amount of material that is ablated at the material, or is it the amount of, or is it Now, if I change from aluminum to copper, can I make a correlation between the ablation threshold of the material and the flyer velocities? But now you're looking at a different density. So this starts to get, so I start thinking about this phenomena as if you change from one material to another, can you start predicting the velocities that you can get? And how does that correlate to how much of the material is actually ablating and how much of it is melting and the pressures that are generated? So we want to build a virtual framework that allows us to predict these kinds of things. So I'm looking at two types of experiments, laser shock. One is where you have an ablator, like you would do at a DCS facility, where the laser is not interacting with the target is well protected, and you can have a shock wave that comes in. You want to generate diffraction patterns while this is happening, and you get information, which is where you get real surface velocities as well. So the idea is you need to have an ability to predict simulated diffraction patterns. You need to have the ability to characterize microstructures while the shock wave is going through the material at different times, right? And you need to be able to correlate all of that with the real surface velocity that you would get in an experiment. So that's my virtual framework to set up to mimic this whole shock experiment. The other one is, instead of having a separate ablator, the laser is actually interacting with the target, which is driving the material as well. And you can look at real surface velocities, you can look at diffraction patterns as well. So there's a whole list of things that we need to have in place before we actually start running these virtual experiments. So I'm going to go through this process. So the in-situ diffraction experiments, we start with using MD simulations, where you can run the shock like you would do in a typical MD environment. You can have a piston that is driven in. At any given time, any snapshot can be generated and looked at using a virtual diffraction. These are packages that are now available for us, where we can look at these things and generate diffraction patterns and start correlating those with the actual microstructure. So I'm going to talk about shock compression and release via the BCC ion, where you get phase transformation and reverse phase transformation over here. To characterize microstructure, we've built a tool which allows us to do texture analysis. I'll talk about that. And then I'll talk about how we have a new method that allows us to scale all of this to the actual length scales of experiments. So looking at samples which are 25 microns, 50 micron systems, and you can generate diffraction patterns like you would have in an experiment. On the laser side as well, we have the same thing. We have a new method which couples a continuum two-temperature model for electron diffusion and heat diffusion onto an MD simulation. So you can mimic laser material interactions. I'll show how we can use this to look at spall failure of aluminum and BCC metals. We can use diffraction patterns for those, and then we can also do the same thing, scaling it up to actually model the material, this phenomena, at the length and time scales of experiments. So I'm not going to go too much into MD simulations. We've done a lot of work in MD on looking at the shock-driven microstructures, a whole lot of effort on FCC metals, BCC metals, and HCP metals. But I'll talk about just a simple setup over here. This is single crystal ion, which is basically on the order of 300 nanometer sample. This is about 50 nanometers on the lateral direction. The system is periodic in this direction so that it mimics a large film. And it's free in these two directions, so the material can expand and you can have release waves coming in as well. So this movie is basically a shock velocity of 1 kilometers per second. So blue is BCC, red is what is phase transformed to HCP phase. The green are all the stacking faults in there. So the shock wave goes to the back end. There's a release wave that comes back in, and you see a whole mess that basically it starts to nucleate voids and stuff. So this is spall failure, where you have wave reflections and interactions at the back end. So you have a shock wave going to the back end, reflecting back. You have a tail coming in, interacting with that reflected wave, and you generate a state of triaxial tensile stress. So you can use this to characterize strengths of microstructures, effects, and see if you change a microstructure, how does that play out. When we've done that a lot, but the focus here is looking at diffraction analysis of these systems. So what we do is we basically take these systems. Now, one of the things to note is running simulated diffraction is a computationally expensive tool. So it takes a lot of time, and it does not scale very well with number of atoms. So running the diffraction analysis for the whole system is a challenge. So the first test was, if we run simulated diffraction analysis of deformed microstructures, do we get similar signatures that you would get in an experiment? So this is your ambient system over here. These are your diffraction peaks. This is your intensity profile over here. This is initially equilibrated 100% BCC. But if we take the shock compressed microstructure and you look at this phase transform region, which is HCP with a whole bunch of defects in them, you look at the selected area diffraction pattern, you basically start getting new peaks as compared to this. And if you look at the intensity profile, you basically get these 3 peaks that you would get for an HCP phase in the system. But so this is an outcome of our stresses. So in real time, we can basically section the system along the length of the sample, and we average the stress tensors, and we plot that to get a pressure profile. So we know the stress state, we know these things, and we can basically identify what peaks are contributing to which state in that sense. So this is shock compressed. You can allow the release wave to come in from the back end, and what this material goes, it goes back to BCC, but this coloring over here is actually showing this. The light blue ones is actually twinned regions in the microstructure. So iron goes from BCC to HCP back to BCC, and in this particular orientation, we actually start seeing twins in a shock released microstructure. These are not deformation twins, so these are transformation twins. And you see the diffraction pattern, you see one broadened peak over here, but there's no evidence of twinning in this, but you do see evidence of twinning in the peaks that are split in the selected area diffraction pattern. So twinning you can characterize using selected area diffraction. The phase transformation you can carry out using these intensity plots, and you will know that okay, this is happening in the system. You can look at spall failure when you have tensile stresses over here, and you see these kinds of shapes of the peaks, and these shapes are basically a result of the strain or the stress gradient that you have. Part of the microstructure is very high stress, part of it is less stress. So all of these are going to contribute to the shapes that you get or the type of broadening you're going to get in the microstructure. So in principle, if you take this whole microstructure and you can generate a diffraction pattern, you can start identifying which parts of the microstructure, which features are contributing to the either broadening or the splitting of the peaks in that sense. So the challenge was this only allows us to look at evidence of these things. What we wanted to do is ask the question, if you're getting twins over here, what is the mechanism of that twinning and how is that related to the phase transformation? And there are no tools that are available that can allow you to characterize these twins differently other than the fact that you know it's a twin, but we don't know what types of twins these are. And is there a correlation between the phase transformed regions that were selected that will give you a twin? CP phase? No, this is twins in the BCC phase. So after it transitions. So this is shock recovered iron showing a distribution of twins. So if we got what is the mechanism of this BCC to HCP back to BCC mechanism that gives you twins over there? So we came up with a new technique which is called virtual texture analysis, and the idea is think like an experimentalist, and build tools like an experimentalist would be using. So we take our microstructures, we basically use something called as polyhedral template matching, which basically gives you quaternions for each atom in the microstructure, and you can use that to basically to generate a rotation matrix like you would have in an EBST map. Okay. And this rotation matrix allows you to look at angle axis pairs, and you can generate a misorientation map or an orientation map. This tool did not exist before, so all we did was just implemented the theory that allows us to build a virtual EBST map. And the idea is similar for each microstructure. You have grains of different orientations. What we do is we generate an orientation histogram for all the grains. Each grain, for example, this one over here, the red ones, these two red ones over here, each of them will have unique rotation vectors. And we can identify different grains by mapping out the two rotation vectors over here. And so this grain has one set of rotation vectors versus this grain has this set of rotation vectors. And this allows you to look at texture or orientation analysis. And you can also do misorientation analysis in regards to a certain grain. This blue grain over here has a different set of rotation vectors over here. So we basically map through the whole microstructure that we would like to analyze. And this allows to look at a grain, this is an analysis called common neighbor analysis, where you can distinguish between the grain boundaries, but this doesn't give you orientation. So our tool allows us to just immediately characterize which grain orientations are chosen over here. We can look at the histograms of those. And when you deform the material, you look at this one where it shows a bunch of twins in each of these grains. So this is the current tool that shows twin boundaries, but doesn't tell you which twins or which types of twins. And we can basically immediately start mapping these different types of twins and look at which variants are selected now. So this allows us to do variant selections in different loading environments, in different microstructures as well. So this is a Python package. We have it ready to go and distribute if anybody is interested in using it. It works with any atomistic data sets. We've done this for BCC, HCP, and FCC metal as well. So let's go back to this microstructure, which is a shock compressed microstructure, and now start applying our orientation analysis for the system. And you can basically look at two different kinds of histograms for the BCC phase and the HCP phase. So you know which atoms are BCC, which atoms are FCC. We can isolate them. So you can see HCP phase, there are clusters over here and clusters. If you remove the BCC and only focus on this, you get four little clusters over here, and each of them have their own rotation matrix as well. So you can plot that, and you basically get in this HCP phase, which is the shock compressed phase, you get four different variants that are selected for the HCP. There's a dominant variant over here, which is blue. There's another variant which is yellow. There's another one which is orange, and there's another one which is cyan. And you can basically look at their counts, their histograms, and everything. These are all have unique rotation vectors. So it tells us that there are four variants selected for this particular orientation of the HCP phase when it is shock compressed. So now you can say, okay, what happens when it undergoes shock release? You can look at the misorientation of this microstructure, which shows a whole bunch of coherent twin boundaries. If you just look at this microstructure, you have no idea which one is a twin. Is this region a twin, or is that region a twin? And we then go back to the orientation analysis and say, okay, this is all the old parent orientation that was already there. So the only things that have changed are these ones over here. The yellow ones. Now, is this one type of twin? Is it one variant, or is it two variants? So you can look at histograms of these as well and look at the rotation vectors for them, and you see two distinct variants that are selected. And you can look at these. So there's a one which is a blue variant, the one which is another one which is a yellow variant. So basically, when you go from the when you're shocking the 110 orientation, you have four variants that are selected in the HCP phase. Out of those four variants, one of them actually goes to two twin variants in that sense. The other ones go back to the parent BCC variant. So, and this again comes down to the actual mechanisms that are based on the Burger's pathway, and you can identify which ones are selected, which orientations are playing a role, and which orientations are giving you twins. So the question is this reverse alpha to epsilon to alpha phase transmission induced twinning, is it only for the 110 orientation, or is that something that can happen in other orientations as well? So we basically run these simulations for different orientations, 100, 111, and 112, and we see in a shock compressed state, we only see one variant for the HCP phase for the 100, but you get three different variants for the 111 orientation, and you get five variants for this. But when they go back to the BCC phase, none of them show any twins. So we basically believe that the twins that are formed after the reverse phase transmission is one of the main important factors is the loading orientation. But this is a single crystal system. So can we start looking into polycrystalline systems as well? But we are pushing the limits in terms of our capabilities of MD simulations, and we know that, okay, the challenge is system sizes. We don't want to look at nanoscale grain sizes, so we want to model large grain sizes. So this is where our next capability comes into play, where we are focusing on mesoscale models to reproduce behavior. And this is a technique called quasi-coarse grain dynamics. And what this is doing is this is basically running the molecular dynamics on steroids. What you're doing is you're saying, I don't want to solve the equations of motion for each and every individual atom. I want to start grouping them together and treat them as representative atoms. So you reduce the number of atoms in the system so you can have less number of atoms, but you mimic the dynamics of the atoms that they would represent. So the way you can think of this as representative volume elements. You take a volume element of a certain number of unit cells. Let's say this is a 2 by 2 by 2 unit cell volume, which has 32 atoms because it's the FCC structure. You can model that with one unit cell, which has 4 atoms in the same crystal structure as you would have in that sense. And the advantage of this method is we can use the same interatomic potentials that we are using in the MD simulations. We have to scale them And that scaling relationship could be anything depending on how much of the volume you want to represent using these atoms over here. So level one, if it is level one, I'm retaining 1 unit cell for 1 unit cell, which is pure molecular dynamics. Level 2 is this scaling over here, where I represent a volume of 2 by 2 by 2 unit cells by 1 coarse unit cell. Level 4 would be 4 by 4 by 4. So it basically means each representative atom is now mimicking the dynamics of several atoms over here. Level 2, you have 8 atoms. Level 4, it is 64, and you can go all the way to level 512, level 1000, anywhere that you want, depending on the phenomena you would like to model. So here's an example of how this works. I'm not going to the
scale the potential for this machine learning develop potential like snap and others.
You can. Yeah. So you're saying how easy is it to use this to
like an EAF?
Yes, yes.
If you have a more general situation like recently.
Oh, yes, so machine learning, but we haven't tried it. I'd like to get my hands dirty trying to replicate. It comes down to how the potential is formulated. If it's an equation that you can use, then yes. If the potential is defined based on atoms and coordinates between them or distances, yes. But if it is something that the machine learning is going to again look at the environments and have a very complicated functional form, then probably it's going to be challenging, right? But so this is just showing simple capabilities. This is a shock of a single crystal aluminum. This is with MD. This is about 40 million atoms. The same system is modeled with 5 million atoms because this is level 2. So you have 1/8 of the number of atoms. So you have a shock wave that comes in. You have a whole bunch of defects. These are all stacking faults and twin faults that are generated. Goes to the back end, hits the wave at the same time, starts to relax, and starts to generate these voids over here at a very similar location in that sense. You're never going to reproduce exact dynamics, but this is giving you capability to run the simulation at a fraction of the cost, because that's what molecular dynamics is, the most computationally expensive system.
How faster it is?
So think about 1/8 means it's 8 times faster, right? Plus our time steps also increase by a factor of the level of coarsening. So you're looking at almost 16 or 24 times faster. So if I want to run an MD simulation that takes 24 days, I can get that done within a day. And I'll show you an example. So the next one, this is polycrystalline system, 720 million atoms over here. Same microstructure, same grain orientation, same dimensions in that sense. I have a shock wave that will come from the bottom end and have the same phenomena of spall failure. The one on the left, just to run this took 21 days. This is level 2 coarsening. It basically got it done in 4 days. This level 4 coarsening got it done in 1 day. And the idea is the same. You have the shock wave coming in, hitting the same system at the back end at the same time, voids and nucleating at basically the same locations in that sense. So this is a quick and dirty way to run a lot of simulations and look at the microstructures and see, is there something that is of interest to you? Then you can go back and do a high fidelity simulation over here.
Where does it break down?
It depends on the questions you're asking. Yeah. So we don't want to look at dislocation dynamics using a high level QCGD simulation. But if you're interested in pressures and temperatures, then definitely, yes, you can use these things. So we apply this for looking at phase transformation like we saw before. So this is a simulation that is looking at phase transformation 001 ion over here, the same system over here, 40 million versus 5 million atoms over here, 1/8 of the system. You run the shock wave, the same idea. You get one variant in both the coarse grain and the level 2 and the MD simulations. The release wave puts it back to the same orientation of the BCC phase. Both of them show a little FCC phase forming. So this is the question whether it's an artifact of the potential or that is actually a state that is generated and you start nucleating voids over here. So the good news is because we are scaling the same potential, we retain all the capabilities of phase transformation, phase stability. The bad news is it will also retain all the artifacts of the potential as well. So if the FCC phase forming was an artifact for that, our model will actually capture that exactly as is. So then we can go back to the same system and look at this. Now this is the 110 because I was talking about the variant selections over here. So I can take the microstructures over here. We can scale them. We can generate diffraction patterns. So this is MD and this is a coarse grain system showing the different variant selections over there. And if you look at diffraction patterns, you see very similar diffraction patterns. So not only can you run the simulation faster and quicker, you can also generate simulated diffraction patterns because, again, these are atomistic data sets. Right? So you get the same HCP phase over here. The only difference is the variant shapes and sizes will be smaller in an MD simulation. This is basically going to retain all of the same variants, but they might be just distributed slightly differently in terms of the actual numbers over here. When it goes back to the HCP phase over here. You get a nice broadened peak over here, and the same thing over here. So qualitatively, it is allowing you to capture most of the important things that is of interest to us that we would like to investigate. So then we apply this coarse grain technique to a real system at the experimental scale. So this is a system which is 8 microns by 8 microns by 25 microns. It's periodic in this direction. So it's a 25 micron foil that I would like to run at DCS, for example. And grain size is roughly about 3 to 4 microns. So this is like an experimental sample that we would have. Now you can run the same shock simulation over here. So you see the HCP phase forming different grains or different variant selections. The back end, and you have the same mechanism over here. So I'm not going to go to the Paul mechanism, but the idea is you look at this, the shock wave and shock release. The good news is now you start looking at these microstructures. There's a whole bunch of twins in the microstructure with grains that are randomly oriented. So first we thought that there's only the grains that are in the 1-1-0 orientation would twin, the other orientations would not. But now we are seeing twins in many of these grains over here. So that begs the question, is it orientation dependent, or is it also dependent on the misorientations with the neighboring grains? So we basically do the same texture analysis for this. So this is our virtual EBSD map for the whole system. And you can have the same shock wave coming in, all the different variants of the HCP phase over here. So each grain will now choose its own variants for the HCP phase depending on its orientation, and maybe some of them will be modified based on the misorientations of the grains as well. So you have, as the release wave comes in, you start seeing these twins over here that are there. So as it travels, the material goes back to BCC. This is a BCC phase now over here with a distribution of twins. And if you look at these different orientations, they're very similar to the shock recovered microstructures that you would see experimentally. So in principle, we are at the time scales of experiments. We are at the length scales of experiments as well. And this texture analysis allows us to go deeper into the system to analyze why these grains are nucleating, forming twins over here. So I'm just giving you an example. You can take different grains and characterize them. This is one grain over here, which is this yellow one over here. When it goes, and you can, let's see if this movie works. Oh, yeah. Oh yeah, it's moving now. So this grain, basically, when it is compressed over here, you get 5 different variants of the HCP phase over here because the way the atoms are arranged over here. And when that grain goes back to 0 pressure, you're basically getting these 2 twin variants over here. So we can go back and start looking at pathways in the material that, okay, which 5 variants were selected and which of these variants now are actually going back to the twin in the microstructure. So this allows us to predict microstructure evolution in real time. And at the end, somebody can take a shock recovered microstructure, run an EBSD analysis and say, this was the orientation of the grain, and here these ones are showing twins and these ones are not showing twins. So again, so we want to do computational guided design of experiments that allow us to do that. We can then do the same thing with diffraction patterns. This is an initial diffraction pattern for the system. This is a shock compressed microstructure. You look at the diffraction pattern as well. And this is your shock release over here, and you get the same thing. So now we have the capability to run the experiment or run the virtual experiment at the same length and time scales as an experiment at DCS. And we can use the data sets to look at diffraction pattern and say, start quantifying how much of the diffraction pattern broadening is because of the phases or the fractions of the phases and which variants and how the twins contributing to that. So one of the challenges I mentioned was interpreting fractions from diffraction patterns is challenging if you have mixed states. So we can take the data sets where you have a partial release state or a partially unshocked material with a shock compressed microstructure, and we can now generate a diffraction pattern for that. And you can look at this as, okay, this is maybe 0.5 nanoseconds before breakout, or this is 0.5 nanoseconds after breakout, and you can start correlating how much is the peak broadening because of that, and how much is the peak shifted because of that, and how much of this peak shape and the thing is because of contributions from the stacking fault, or the contributions from the twins in the microstructure. So that is the analysis we are doing currently. We're building machine learning models to correlate fractions, phase fractions, defect fractions to the actual diffraction patterns. This is an effort that's going on with Remy at Sandia.
What happens if you shock it so hard you start to melt?
So you can get you can get a diffraction pattern for the liquid as well. Absolutely. Yeah. So and that is something we are also looking from the laser side of it here. So the next thing is can we now do the same thing for the laser material interaction? So here it was just a piston coming in, the sample was not interacting with the laser. So we have a method called an MD TTM method where the MD system, where's my, oh yeah, the MD system over here is basically overlapped with a continuum 2 temperature model. So this allows you to mimic the effect of, or the idea of having electrons in the system that absorb the energy, and that energy is then translated onto the lattice through electron-phonon coupling that allows you to actually generate laser ablation, melting, and shock generation as well. So all of these parameters over here that we use, these are basically parameterized using DFT simulations where you can include temperature dependence as well. So this is the setup that we have. This is laser shock compression of aluminum over here. The idea is you have a slab, the laser comes in, we use experimental conditions. So there are some experiments which have been done at sub-micron size dimensions. The fluence is 13 kilojoules, the pulse duration is 150 picoseconds, and we can run the same simulation. So this is a shock of aluminum, and we are only looking at the microstructure. So all of this is actually ablated material that is pushed out, and the shock wave is generated in. Aluminum EM for this orientation actually shows a BCC phase, which is an artifact of the potential, but that kind of goes away as the wave hits the back end of the material, and you basically start seeing the phenomena of spall failure. The idea is the tail of the wave and the release wave interact to create this region of tensile stresses where you start nucleating voids. So you're recreating that experiment, but this is a femtosecond laser experiment, and most of the experiments we are interested in is on the order of nanoseconds. We can do this for microstructures. This is aluminum. Again, this is the plasma, the ablated region that is pushed out. It starts to generate a melt region right over here, and a shock wave that's traveling all the way to the back end. It hits the back end, starts to expand, and we can basically characterize the stress distribution. So sometimes you'll get ablation and spallation at the front end, depending on the laser fluence that you have. And you can basically characterize the stress evolution, the stress wave, the wave, the shapes of the waves that are evolving. You can look at the time histories of these. You can look at temperatures that are generated during the simulations as well. And you can start correlating the temperatures with the laser fluence, just to allow us to start correlating with let's say hydrocodes that are predicting temperatures that are generated as well. I think this is information that is very difficult to characterize using experiments. So if we can correlate that, it'll be great. So we have a source term. So we have a source term over here, and we can give it a Gaussian profile, or we can give any kind of profile that you would have in an experiment, and we can just implement that. Source term for energy. So you'll say that, okay, you can have a top hat profile that is spatially distributed, but you'll also have a temporal profile for the laser. You can have a square pulse, you can have a sharp Gaussian, you can implement that. And that profile tells how the electrons are going to absorb the energy as a function of time.
You calculate the laser ablation.
Yes. So given the source term, the model predicts whether or not it is going to ablate. And that's the energy, how much energy is deposited. And we take into account the reflectivity of the metals as well. For aluminum, 90%, tantalum, 30%. And we can add that to the model. Consider this reflectivity, and you'll see what you get.
To ablate, is it able to account for, the change absorption happening at different depths?
Yes, so we have certain models, and we'd like more information as to what effects should be accounted for with this. So our first models were once it's ablated, the atoms don't interact with the laser. The next model was it continues to interact with the laser, and that again changes the dynamics of the ablation plume as well in that sense. So no, good.
Or any effects of radiation from the ablation front going into the.
Yeah, no, we do right now because our focus more has been on what happens at the back end once you get a shock wave. But if that is something that needs to be embedded, we can think about adding that in the source term, or how the electrons are going to absorb the laser because of that. But yeah, love to talk to you about that. So this allows us to do this. We can do this this is aluminum. We do the same thing for tantalum, and you get the same thing. We parameterize laser absorption for tantalum. All the temperature depends on the heat capacities, thermal conductivities as well. And we can look at we can measure the pressure wave propagation. We can measure the temperatures in the system as well. We can measure the kinetics of the solid liquid interface as it is propagating as well. So this allows us to recreate those things. So the next thing is you can use this to generate diffraction patterns of the same systems over here. So again, we are taking small sections for these systems because of the computational cost associated with it. But it allows us to look at selected area diffraction patterns or these intensity profiles, and you can start correlating the role of microstructure on the shifts of the peak or the broadening of the peak in that sense. So one of our current efforts is to come up with ways to combine diffraction patterns from different sections of the sample that allows us to recreate the system, the whole diffraction pattern. So you'll have a liquid phase and ablated phase and everything, and see how does that actually correlate to a full diffraction pattern as well. So this is now mesoscale modeling, the same thing, coarse graining. We want to do the same thing. So this is our aluminum system that I just showed. This is now modeled with our coarse grain system. So all we are doing is replacing the MD with the coarse grain system. The electron dynamics is still the same, the two temperature model. You still see that BCC phase that was formed over here. It was retained in our potential. You see the same ablated volume over here. You still see similar interface between these things, and you see similar dynamics of void nucleation as well. So this allows us to start testing, okay, can we now scale this to higher levels of coarsening in that sense? So we take the same system and we start looking at, okay, if you have MD simulation at a certain amount for the certain fluence over here, which is defined by what we think is available experimentally, we can run the same system at different levels of coarsening. So one of the things to keep in mind in coarsening is also, just like you have size effects in MD simulations, you have size effects in our coarse grain simulations. So you need a certain minimum thickness of the sample to make sure the dynamics is reproducible. So we build so whenever we are comparing with MD, we have a certain minimum size of the system as well. So in all of these things, you see a certain ablated fraction, you see a certain melted fraction, you see this artificial BCC phase over here in MD that is retained across all the levels of coarsening over here. You can track the evolution of pressure for the different levels of coarsening, and you see some deviations as you go to higher levels, and these deviations are in the ablated region over here. But if you see as the shock wave shape and the location of the shock wave are very, very close in that sense. So this allows you to just look at this at a fraction of the cost. The lattice temperatures, again, slight deviations in the ablated plume right over here. But as you're looking at this region, you know that the temperature distributions along the length of the sample is very, very close. So the idea is you can recreate these experiments at realistic scales. This is our first set of simulations, and over here what we're looking at is shock loading of aluminum. This is polycrystalline sample, 1 micron by 1 micron system. So this is periodic in this direction over here, still a femtosecond laser pulse. And you get an ablated volume over here, a shock wave comes in, there's a lot of defects, the back end starts to expand, and then you get a lot of defects over here, and then nothing happens. We don't see any voids nucleating at all for the same system. And then we looked at the microstructure. Again, let me just blank out all the BCC, all the FCC atoms. And what happened was, as the wave comes in and this starts to expand, you actually start seeing voids nucleating in the middle of the sample. But as the simulation continues to evolve, they actually go back and close. So if you're just looking at the microstructure from outside, you don't see any voids. You're like, okay, it did not spoil at all. So we basically go back and look at the pressure profile. So all we are doing is looking at the stress as a function of the depth of the sample as a function of time. And you see a shock wave comes in, reflects back, generates this tensile zone where you have voids. But this tensile wave interacts with the solid liquid interface and reflects back to create a compression wave. So it undergoes a recompression, which actually closes down all the voids that were nucleated. So they were not allowed to go completely and start to initiate failure. And this recompression basically gives you a signal in your real surface velocity profile over here, because now you have another compression wave that is coming in. So people have designed recompression experiments where they have a second impactor coming in, and so the intensity or the wave stress depends on what is the impedance of the other material that is coming in. You have a solid liquid interface, so the intensity of the wave is not as much, so you don't get a very high velocity in the recompression wave. But you can track the number of voids in the system, and you can look at the void fraction over here, and you can see that, okay, the voids initiate at a certain time, reach a peak value, and then they go back over here. So the next thing and the final thing is basically then thinking about the laser-driven flies. The same idea over here. We have samples now which are 25 microns and 50 microns. We are driving them with a laser of 134 joules per centimeter square, pulse duration of 10 nanoseconds. And you can see that the ablated plume is actually driving these flyers away, which is what you're typically getting in an experiment as it interacts with the laser. So what I'm trying to say over here is we have now the capability to mimic these experiments and actually have characterize the acceleration of the flyers. You can look at temperature profiles over here and see this as a function of time. What are the pressures that are generated? What are the temperatures that are generated? And what is driving the flyer actually to the back end? You can look at the back end like you would do with Weisar analysis, and you get these real surface velocity profiles. You can look at effects of microstructure and effects of thickness. So the smaller samples will basically accelerate a lot more than the thicker samples over here. So we are looking at data generated from real experiments, which will give us real surface velocity profiles. And we want our models to say, for these velocities that you're getting, how much was the ablated volume, what are the temperatures generated, so that you start making correlations between what is happening in the material that is giving you an outcome in terms of real surface velocity profiles. So with that, I'd like to summarize what we have been doing. We use MD simulations using virtual diffraction that allows us to characterize plasticity contributions. We have texture analysis, which is a code that allows us to look at phase and twin variants in microstructures. We have a method that allows us to model laser material interactions so that we can mimic experimental conditions. And then our coarse graining methodology basically is a low fidelity methodology that allows us to actually map the length and time scales of the experiments, and also allows in situ diffraction. So one of our efforts is looking at building digital twins of these experiments. You can run a lot of experiments, generate a lot of data, and start making correlations over here, and also build a database of diffraction patterns of different stress states so that you can start identifying the contributions to plasticity.
Can you predict phase transition kinetics? How long it actually takes to go from one phase to another?
Yes, we can. We have the information. We haven't quantified that as yet. But if it is in these experiments, we can. If it is something that is observed in an experiment.
Well, there's examples. So on the NIF laser, we have a ramp compression that keeps materials solid.
So yes.
High pressure.
Mm-hmm.
There's interesting examples where there's very slow kinetics where we never see a phase transition that should be there.
Okay.
Where we hold the peak pressure for maybe 5 or 10 nanoseconds.
Okay.
Okay.
It never doesn't transform.
Whereas other materials like
Iron, yes.
happen so fast you
Yeah.
can't really measure it.
Yeah.
And there's everything in between.
Yes.
Can you actually make predictions of kinetics?
Yes, we can. We can. I mean, the microstructure is there. We can look at a series of snapshots and saying, okay, this certain volume, which was initially FCC, as the wave comes in, you know the rise times of the waves, and you can see how long does that whole thing take to transform. From our simulations, it happens instantaneously, even in MD simulations. The only thing, the issue I have is this is all governed by the potentials we're using. So the kinetics predicted by the potentials is what we would capture, but it gives you a ballpark figure as estimate in these systems as well. The reverse phase transformation is something we know it's a little slower than the forward phase transformation.
This single crystal diamond.
Yeah.
You predict the phase and you take it up to a pressure well above its trend.
Yeah.
Predict the transition.
Yes.
EC8 phase.
Okay.
Predicted it should have transformed in a,
So if the potential is fit to predict that phase transformation, above a certain pressure and we drive it to those pressures, we will see it here. So it comes down to here.
The potential.
Yes, yes, it does. So our capabilities are limited by the potential.
In that sense.
Yes. Sorry. I mean, my assumption is, yeah, the assumption here is we believe in molecular dynamics and we trust these potentials. That's when we can do all of these things.
Train the machine learning.
Machine learning algorithms in that sense. Yes. Yes.
Glad you brought that up.
Yeah.
I was just heading there. I want to jump into sort of some of the most exciting research we're doing here. It's with a ramp compression.
Yeah.
The difficulty there is that the ramp extends over a few nanoseconds.
Mhm.
It's not all sharp.
Yeah.
But it allows you to get into, very high pressures where there's much more uncertainty in what's going to happen.
Absolutely. Yeah. So, I
If you
mean,
could get into that,
Yeah.
it would be just good for. It would connect you to sort of really the frontier of the high pressure stuff.
I would love to try that. I would love to try it out. So,
Fertile territory. because
Yeah.
Things we look at weren't predicted or
Okay.
we struggled to try and explain. And
Yeah.
some things we still haven't.
Yeah. I mean, I've always thought that, okay, these new phenomena, it's always best to start with systems that you know are well tested. Yes.
What you're doing is really, really nice.
Thank you.
It's nice to sort of push that.
Push that
into our
envelope.
territory because
Yes.
there's- we still are scratching our heads about
Yeah,
targets.
yeah. No, I keep telling the guys who develop machine learning potentials, make it easier to implement so that we can do things with it. Right. So, anyway, just conclusions. I want to acknowledge NNSA for funding this, and this has allowed us to build all of these capabilities. Collaborators, Sergio, Atlanta, oops, sorry, nope. Sergio Atlanta, Remy Sandy, and Mukul and John over here who've been very kind to help us out with these things. So, yeah. Thank you.
Thank you very much.
I have another question.
Yes.
Early in your talk, I think I saw you say that there was flyer plate experiments done at Johns Hopkins.
Yes, yes.
With a laser-driven flyer plate?
Yeah.
Is that what I
Mhm.
Who's doing that?
Katie Ramesh.
Well, it's time for me to visit again.
Yeah, so I spent the last,
Very good news.
Yeah.
Very good.
he's been doing that for a few years now. His student,
Last time I visited, there was none of that.
okay, yeah, so I did a sabbatical with him the last 6 months. And the reason I went there was we have the models that we can predict these things. And his interest is more on the shock and spall side. So I said, can you run these experiments? Like, you want to do a sabbatical? Just come here and do these experiments. So that's why, and when you start running these experiments, you start understanding how things are being analyzed, how samples are prepared, and what are the nuances with that. So I was telling Paul, I have newfound respect for experimentalists who generate good data. I know it's extremely challenging to generate good data. Yeah, so really enjoyed running those experiments. And we're like, okay, now let me try modeling those phenomena in that sense. Yeah.
So there are a few questions online. So somebody, Vasily Bulatov asks, in your fully resolved MD simulations, have you populated your initial crystals with dislocation sources? And his question is especially relevant for simultaneous simulations of shock in
Yes.
Single crystals.
Yeah, no, we haven't. Well, we have added, not in this work, but we have added dislocations to single crystals to look at the effect of dislocation density on the decay of the shock wave as it travels to the material. So that allows us to see how a shock wave interacts with pre-existing dislocations, and we observe that the decay is much faster in those, and it modifies the dynamics as well. It also actually strengthens the material in a certain way in terms of void nucleation and damage evolution, but not in this scope of work.
Thank you. And there's also a question from Ivan Olninik.
Ivan.
I might have missed this, but what and how do you coarse grain if you use the same interatomic potential to describe interactions between new cells containing many atoms? How do you then determine the phases, BCC, FCC, defects, etc., without knowing local atomic environment of each atom explaining the main idea simply would be greatly appreciated.
Okay, I don't have a slide on that, but the idea, Ivan, is that you're basically running an MD simulation with representative atoms. So what we do is we know that in an EM potential, the energy of one atom, let's say this corner, is determined by the surroundings. So how many nearest neighbor atoms does it have? What are the second nearest neighbor atoms, the third nearest neighbor atoms, and so on. So all we do is take the same volume, and we basically tell this atom, which is a representative atom, that it basically has the same surrounding as it would be. The only difference is the atoms are at a certain scaled distance from each other as compared to an MD simulation. So what we do is we recalibrate, not recalibrate, we scale the potential to have a minimum at the scale distance. So this is twice the distance over here between the corner atom and the face-centered atom, let's say, as compared to the distance in an MD simulation. So all we are doing is a simple scaling of the interactions over here. So we normalize it by the level of coarsening, and we can reproduce the equation of state of the system. We can reproduce all the phase energetics as well. The defects is a slightly different thing. It will still nucleate defects, but the nucleation energy for defects is a collective nucleation energy for many defects. So you're looking at this methodology where you can have dislocations that are generated in the coarse grain system, but each dislocation basically means that the system has had enough time to nucleate many dislocations by that time. So instead of 10,000 dislocations, our coarse grain model will roughly have maybe a few thousand dislocations. But that scaled energetics accounts for you to get the same stress released due to nucleation of dislocations, and that we are able to reproduce the full dynamics of the shock wave while this is happening. So I'd be happy to talk to you separately on this as well.
And there's also a question from Saranj, who says, what is the orientation resolution of the template matching method? Can it resolve the small changes in orientation within a single grain upon shock?
Yes, we can. So anything where you can identify a cluster of atoms that are together, where they are not identified as disordered, where you see an orientation, we will capture that as well. So anything around the order of a few nanometers, we will see those things as well.
And also, I was curious about something. In your simulations, are you able to control statistics, or have you been able to look at statistics of the various orientations of the grains and how big they are, and various angles and shapes? And can you control that by adjusting the shock?
I have a nanocrystalline one here. So our nanocrystalline systems in MD, or the polycrystalline systems in this, these are all based on random orientations. So we build the structures using Voronoi tessellations, where we specify grain size and we specify a random orientation. But if you want texture, we have done texture where we say you want a certain texture orientation in the system, and we can build those things.
So there's no correlation amongst neighboring grains?
No, this is just randomly generated grains in that sense. And if you have a large number of grains, you have more or less all kinds of orientations incorporated in them. And the grain sizes also, we can impose any distribution that we would like to have as well. If you want a lot of small grains and a few large grains, we can do that. We didn't find the need to explore that avenue today. The focus is more on looking at the shock response.
You haven't taken CT scan. Have you taken CT scan and put them in such systems?
Not yet.
Of actual material?
No, not yet, because so far we didn't have the capability to take experimental data, which is large grains. These experimental data would be like few micron size grains or 10, 50 microns. We can't do that with MD simulations, so we never bothered to do that. But now that we have the capability, if there was an experiment where we're going to run that, you can characterize the microstructure well in advance. If you have a CT scan, we can import all of those orientations and build microstructures with the same orientations, shock the material, take diffraction patterns, and you run the experiment and look at the recovered microstructures, and we'll tell you what we think is a recovered microstructure as well. That is the big plan. Hope for us to recreate these experiments.
So just a note, I can't hear people who are online. So McCall, if you had a question, can you type it out?
Yeah, I do. Interesting seminar, Avinash. I have a question.
So I was interested in your two-temperature model.
Okay.
And so if you input a particular laser pulse and a particular initial configuration for the material, how close is the surface velocity to, say, a measured Vizar in that same kind of experimental setup?
So that's a very good point. So what we have, I don't think I included that just for time spent on more on the objectives of the work rather than quantitative data. But all of our simulations, like for example, these simulations, we get Paul strengths which are very similar. We get real surface velocities, particle velocities, which are close. There are differences. One of the main differences in these systems is a lot of the experiments are run where the sample is mounted on a glass substrate. Right? In our models, we don't have a glass substrate yet. So either the sample is grown on a glass substrate or there's an epoxy. So our model does not take into account glass or epoxy. So when you have glass or glass substrate, when the material is ablated, the plume cannot expand. Our system allows free expansion of the plume. So we get slightly lower pressures than you would get in an experiment. So the real surface velocities we get are slightly lower than experiment. And the next step for us is if there are experiments with a glass backing for the substrate, then that would kind of push the pressure up a little bit, and it will also generate higher pressures and a higher shock wave. So the velocities are slightly higher. So it's the same thing with these laser-driven flyers that we have. Our velocities, these velocities that we are getting, these are on the order of 100 to 1200 over here for these systems. And I think I had a plot somewhere for our experimental data. Those were similar, but our numbers are slightly less. And I think it's because our plume is allowed to expand completely freely. And if you stop that, then there's going to be a slightly higher pressure, and it'll push the velocities a little bit higher. So that's what we want to validate is because it's difficult to mimic a glass interaction and an epoxy affecting the plume. So we want to calibrate that model to give us the right velocities. Yeah. But the particle velocities, at least in the sub-micron scale experiment, they're very close. So we have that information published. I can share that information with you. Yeah.
Okay, I think we should, or one quick question, or
I can pass it up to him.
I have another question.
Yeah.
Over the last couple of years, we've encountered an effect here that is very real and also affects a lot of previous experiments and experiments under design. And it's the following. Typically, when we do our experiments on lasers, we have a material that we put in there as an ablator, and then we have the actual material of interest on the back of the ablator, and then they be tamped with a window on the backside. And then we also do a lot of ramp compression. What we discovered is that in ramp compression, if you have a plastic ablator, you can start forming nano regions of nanodiamonds in the carbon. The carbon in the CH can be pushed into a nanodiamond setting.
Interesting.
So what had been just something convenient to turn laser energy into pressure, was the plastic. And then the pressure pushes and we go on with our experiment, suddenly has a bunch of nanodiamonds in it. And that raises all kinds of questions about experiments we've done over the last 20 years because we've used plastic ablators forever. And so my question is, to get nanodiamond in plastic, you need either a ramp compression or two-stage shocks. The density is a little bit higher and it's not quite so hot. Can you predict the generation of nanodiamonds in two-shock driven plastic?
We can set up the models.
We could start saying, would you check this? Is this design going to go through that diamond formations where it just complicates the interpretation of the experiment immensely?
So I'll say this: we can set up a model to do a two-stage compression or a ramp compression as well. We can use the potential for diamond as well. Now the question is that formation of nanodiamonds triggered by the plastic? Is it just the wave effects, that the pressures that are generated, or is it the pressures and the temperatures that are generated over there?
It's probably both. It's Dominic Krauss, what was it, a Nature Photonics, Nature Astronomy.
And so,
it just knocked us back on our heels.
Your hydrogens move one place and your carbon moves another place, and then you get the right pressure conditions.
And some of them survive even on release. Pick it up and they're there.
Oh, wow. Okay. That's a complicated system for us at this stage. If it is clean carbon, and if I can simplify the system, let's say I can use an aluminum ablator and do it, would you get the same thing?
Say that again?
If I use an aluminum ablator instead of a plastic ablator.
No, none of this happens then.
Yeah. So,
We-
yeah.
Beryllium ablators, like.
Yeah.
Like to switch. Oftentimes we're saying, like, beryllium is a very good ablator.
Okay.
But, it makes the experiments harder because it's a, poisonous
Yeah.
material and,
Yeah.
and the target fabrication is harder because now you have to deal with touching
Yes.
beryllium. and
Yeah.
So everything gets harder with beryllium.
So for us, then we have to have a model that mimics laser interaction with the plastic. And
Not
then
the
you're
la-
like,
It's not the laser, it's pressure, it's two-stage shocks.
yeah,
The laser is just the means of generating the shock.
The
You
shock.
just need two-stage shocks.
yeah,
If you look at that Dominic Cross papers, it's just two-stage shocks. You just need to get into the right density and temperature regime,
okay.
and then these
Yeah.
things form.
I'll have to look into it, but it comes
It would
down.
be fascinating. It'd be a wonderful paper on your part if you could
They
take.
do some atomistic simulations, but we'll have to look at exactly.
Yeah.
what kind
If you give me your email address, I'm gonna go find his first paper on.
Okay.
There's
I'll
probably more.
definitely look into it.
Because it's
of- I
just,
think he has time in his schedule later today.
thing is, I can't, for some reason in NIF, we can't print. I
I
can't
can't
print.
print.
On Macintosh, you can't send anything to the printer anymore.
Well,
Okay.
So-
All right.
But I can show it to you.
Yeah.
Dig it out.
Yeah, I'd be happy to look into it. My
Wonderful demonstration of your capability. You can actually show.
Can we
it.
finish the conversation offline? Let's let people go. Thank you so much for attending, and I hope everybody comes next time, and hope everybody has a great rest of their Thursday. And let's thank our speaker again.
thank you so much for everything. Yeah.